Welcome to the CCSS meeting, and this is number 62. And usually we do lunchtime because today we're very honored to have Jorge here. That's really the east coast of the US. So it's 7 o'clock in the morning there, so we make it as a dinner event. I hope also you like it this way. So this is the talk over the thing, that's the neural differential equations, and there's the applications in complex systems. For the people, probably some people the first time heard this or some of you already follow the series of this talk. So basically, we know that machine learning, many tools are considered as black box. And with this, the neural differential equations, they try to combine with the white box. Actually, I copied it from Jorge's abstracts. So like the dynamical models. So they want to combine it and make it like a gray box. So for more introductory talk, you can always refer to our first talk of this series, now already published on our YouTube channel. That's given by Dr. Patrick Keecher. That's the mathematician from Google X, and they give a nice overview over this tool. So you can always refer to our YouTube. And today is the third one of this series, and the second one was about applications to atmosphere models. And today we come to ecological data. So we are very honored to have Dr. Jorge Arroyo Esquivel. Sorry, that's for the pronunciation.
Yeah, it's Jorge Arroyo Esquivel. Thank you.
Yeah, okay, thank you. And he is a postdoctoral fellow in the Department of Global Ecology in the Carnegie Institution for Science. So we're also very curious about your applications and also talk about this in general, this neural differential network and also applications to ecological data. Thank you. Floyd, as yours.
Yes, thank you so much. Yes. Well, thank you for coming to my talk. Good afternoon for you. Yeah, let's get started. I'm gonna get started by just giving a pretty brief overview of what specific issues do we have with how we do models of ecological systems. Natural ecosystems are pretty complex. There's a myriad of different factors that come into account when you are considering nature, long food chains, complex food networks, complex interactions with the environment, with other populations. And that makes us observe a lot of complex dynamics that we predicting with models, but they are actually happen when you go and you observe the data. There's a lot of nonlinear attractors. There's bistable systems, which in ecology we call alternative stable states. There's long transients. So here long transients is that we may be in a system that a transient may happen for decades. And maybe we're only sampling for like 1 or 2 years, and we're not able to discern between a long transient and an attractor in our dynamics. We have other sources of complexity. We have some systems that are better described using discrete time models. And there are some others that continuous time models work better. We have a lot of variation in space and time, and stochasticity is an everyday event. Well, it's no surprise that ecosystems are highly variable due to environmental conditions, and one of the biggest stochastic processes that we may consider is weather. Weather may affect the dynamics pretty significantly. So basically, this slide is just a summary version of ecology is way more complicated, and that forces us to do some reconciliation when we're thinking of using models. Well, based on the previous slide, you can imagine that ecological models are, if we try to do all of the things that we need to do to have a realistic ecological model, it will be highly intractable, computationally infeasible, hundreds and hundreds of different variables interacting with each other. It will be a nightmare. So we have to use simple models instead. But simple models, because of how complex our systems are, we are just modeling a small portion of the dynamics that are actually happening. And that may lead to modeling bias. So it's more likely than not that we are omitting things that are actually important in our models. And even if we had, in many cases, we can use we can get a lot of information out of these simple models. But even simple models are hard to parameterize, and the data requirements can be intensive. So during maybe like the last half of a decade, maybe since 2015, a lot of progress has been made on the trying to do trying to reconcile all of these different issues to explain ecological data using maybe black box models. And today, I'm not going to talk to you about that part of the history. I'm going to talk to you about what's happening now. What are we looking forward to? And I'm going to introduce the concept of scientific machine learning. So this is a machine learning paradigm where we are using neural networks, and they are incorporating some the knowledge of the nature in the data. How we do this is that we incorporated by telling the neural network, hey, we have this model, this simple model that explains partially our data. Can you use that to learn the rest of what's happening in what we're observing? And there's plenty of ways to do this. You can adjust your loss function to incorporate that knowledge. You can change the architecture of the neural network. And there's a lot of hybrid modeling being done as well. There are several methods that exist in the literature. I'm just going to briefly talk about physics-informed neural networks, which is just a regular neural network, your favorite deep learning algorithm, but on your loss function, you're not only learning the difference between your data, but you're also learning that the neural network is producing a time series that is also satisfies the differential equation of the simple model that you may have. And for the rest of this talk, I'm going to talk mostly about neural ordinary differential equations, or nodes, and some of their variations, some of their expansions. And there's plenty of other non-named methods. Maybe they were used for one or two studies, and they haven't picked up a lot of steam on the literature. So there's this good review by Wheeler and collaborators in 2022 about the different methods of incorporating natural knowledge into machine learning. Why neural networks? Well, there are non-parametric statistical models, and so that means that they don't assume a form of the function that describes the data. So they kind of overcome the modeling bias that we may face when we're looking at our data. And also, they are universal approximators. They can approximate any continuous function with enough data. So the hope when we're using neural networks is that whatever we do is enough to get a good approximation of reality using, because we're assuming that reality is continuous, and then the neural network can approximate it. So now let me define nodes. we're going to have a neural network that we're gonna write as double N, that's gonna take X as an input, which is a system at a given time. And it has some weights that we're gonna define by big theta. And a system of nodes is a dynamical system that is described by this neural network. So here we have a time series X that's we're using a neural network not to learn the time series itself, but we're trying to learn a differential equation that describes the time series. So we want to find weights that make when we're trying to solve it using numerical methods for differential equations, we want to have this neural network be a good estimator for our time series sample at time t. And I'm also going to talk about one of the biggest expansions of nodes that we have, which are called universal differential equations, or UDEs, in which we ask the question, what if we know something of our system, right? We have all of these simple models that we've been used to describe ecology for over a century. Why don't we just incorporate it into the neural network as well? So let's see that we have a parametric model that partially describes our system. So this could be a linear exponential growth. This could be logistic growth. Maybe some interactions between species that we know beforehand. And then we have a system of UDEs now, which is a dynamical system that incorporates both the known dynamics through G and the unknown dynamics through a neural network. So basically here, what we have is that now we have a differential equation where we partially know the dynamics through this function G, and whatever difference between G and the real dynamics of our time series is going to be absorbed by this neural network. So this helps us have the best of both worlds. We can get all of the information that we have from our function G, and we're learning new things with our neural network. And well, this is all good, but we have a problem about black boxes, right? Non-parametric models can often become black box models. So that means that we don't know what's happening underneath the neural network. But the nice thing about nodes is that they encode the neural network as a dynamical system. And we have a lot of different tools from dynamical system theory that we can use to learn and understand what the neural network is doing on the background. So people have done, for example, look at equilibrium points, trying to do stability analysis of the trained neural networks, and you can get a lot of information out of them. I could have another talk just talking about the different techniques that we can use to interpret what the neural networks are doing when you put them when you make them nodes. But I'm just gonna briefly talk about the example that we have in ecology, where this paper by Bonafé and collaborators, they infer the interactions between two populations in a predator-prey system. So just gonna pretty briefly talk about what this model looks like. We have a population of a predator, X, and a population of a prey, Y. And we have this Lotka-Volterra predator-prey model that you may have seen in a class in dynamical systems, in which the predator population is decreasing exponentially and is being consumed and is consuming the prey at a rate gamma. And the prey is dying by being consumed, and it's growing exponentially. And for those of you that haven't seen this model or its dynamics, this is one of the most classical examples that we have observing data. So we are, for example, this is a famous data set from the early 20th century, where people were keeping track of Arctic hare and lynx populations through the years, and they were seeing this cyclical behavior. And this cyclical behavior is actually predicted by the model I just showed you. And what this paper found is that a node system is capable of understanding the interaction between the two species. So, for example, the hair growth rate, when the lynx densities are higher, they found that the hair growth rate is actually uh, is actually negative, is decreasing, and vice versa. You can see that as the lynx becomes positive, as the hair density becomes positive, the lynx growth rate becomes positive too. So they were able to find these interactions that, I mean, we have known them for more than 100 years, but it's interesting that this was found using a neural network. So you can interpret what the neural network is saying, and what it's saying, it actually makes sense in the ecological context. But I promise you I was going to talk about forecasting, and that's what I'm going to do. So for the rest of the talk, I'm going to talk about how do we use these scientific machine learning methods to perform forecasting. And it's a pretty an increasingly more popular topic in ecology. We're interested more and more about trying to do ecological forecasting. There's a lot of initiatives that are aiming to create ecological forecasting systems that hopefully someday in the future will be comparable to what people do with weather forecasting, for example. That would be awesome, but that's still a long way to go. And we're trying out different methods, different techniques to try to come up with a forecasting system that works just like that. So to test this, we generate synthetic data from a model of competing populations. Well, from Kramer and Klausmeier, which is we're keeping track of populations N, and they have a growth rate function that is all of the populations have the same growth function that is uniquely defined by this parameter Z. They are all competing for a resource, and they are all sharing a common mortality M. And we have this parameter, that's the per capita growth rate, and the parameter lambda is just a small parameter to make sure that no population becomes extinct, just for numerical stability of the neural network. We incorporate observation noise using a normal distribution that's proportional to the population density. And that helps us, this model helps us create synthetic data with observation noise. So the synthetic data that we're going to try to use for forecasting is this n hat. That's the solution of the differential equation plus the noise. And of course, we don't have negative densities in ecology. So if it's smaller than 0, well, we just put it up to 0. And we're going to train nodes and ODEs, and to overcome noise, to overcome the possible issues that are caused by observation noise, we incorporated spectral regularization. So this shows that the loss function is the root mean square error. So the error squared, the difference between the prediction and the real data, and alpha times the operator norm of the weights. So we can think of the neural network weights as a combination of matrices, and the operator weight of the neural network is just the product of the spectral radius of those matrices. This is just an addition to help overcome any issues caused by noise. And we also test two types of nodes and ODEs. So one of the interesting questions that we have here is that this model is non-autonomous. So there's a time variable forcing function that changes the dynamics through time. So we wanted to incorporate time into our neural network to see if making our system non-autonomous will help in any way to improve the forecasting performance. So time aware, they receive time as an additional input. And time agnostic, they don't receive time. That's the only difference between them. And we're testing for UDEs, our known function is the shared mortality by all populations share the same mortality, maybe through some flushing, some in selective calling. And then, so we're saying that the UDEs, they know that all populations share this per capita mortality. And we're going to test performance, and I have a 3 in this slide. I apologize. We recently received comments from a reviewer, and we now have 4 metrics. So we test using the root mean square error. So that's what we call accuracy in forecasting. The size of the confidence intervals, that's what we call precision. And then we have an interval score that's it's a pretty new metric for forecasting performance, in which we're basically seeing that maybe some models are not the most accurate or the most precise, but when you consider both accuracy and precision, they perform better. So basically they can overcome the issues caused by the lack of accuracy or a lack of precision. So this interval score accounts for a lot of these issues. And we also wanted to see ecological interesting performance, and we wanted to see if we were able to predict the final community size. So just remember that I was talking about how we had a small parameter to make sure that everything was numerically stable. But so that means that some populations are just persisting because of that small parameter. But we were interested in seeing if we can find if we can have we can predict how many species will actually have dynamics in their system, will actually be at considerable densities. So we wanted to predict that using the different methods. And of course, if we want to test performance, we have to compare it to something. So we compare their performance to simple ARIMA models. Autoregressive models are pretty standard in forecasting, so we tested with them. A method that's highly used in ecology, is highly popular in the ecological forecasting field, called empirical dynamical modeling, is basically what's the state of the art in ecological forecasting. I'm not gonna go too much into detail about these state of the art methods, but here are the references if if you want to read more. And long short-term memory models. So this is just LSTMs, the basic recurrent neural network. We also wanted to try to compare their forecasting to it. And yeah, let's see how this works. So here's a slide just to showcase some of the dynamics that we observe in the system. You see on the top we have the three comparison methods, and on the bottom we have our nodes and UDEs. So one thing that and the dots are the data, and the lines are the predictions, and the ribbons are the confidence intervals. So one thing that you're gonna see when you look at the UDEs, for example, is that the UDEs, they are predicting that the populations go extinct. That was a big surprise for us. The nodes kind of know that there's a variation in the there's small oscillations in the data, and LSTMs and EDMs, they are kind of constant. Just wanted to remind you that all of these models are on tune. Of course, there's different ways to tune the different algorithms, but we wanted to have a fair fight between all of them. But one of the nice things that we were observing is that the nodes, they have a small, they have a higher precision, at least when you look at the time-aware nodes. Of course, this is just a figure to showcase the time series dynamics, but let's actually look at the methods, right? When we look at accuracy, so this is the root mean square error. You see that EDMs, as expected, they're the most accurate method, and nodes by themselves, they are kind of comparable to LSTMs and to ARIMA models. So at least they are not significantly worse. UDEs, on the other hand, they had a pretty rough time. One thing that's interesting is that nodes, when you consider time-aware nodes, they don't seem to have that big of a difference. Whereas UDEs, being time-aware kind of improves a lot their accuracy. So that was an interesting result there. Precision wise, so this figure is a little hard to see, hard to read, but the solid lines represent the maximum size of the prediction intervals, and the dashed lines represent the minimum size of the prediction intervals. And as expected for ARIMA, they are growing exponentially. Nodes and UDEs, they kind of stabilize a little bit before, and LSTMs and EDMs, they are more precise in general. That was kind of expected as well. But what we were not expecting is that when we look at the interval score, and this is a trade-off between accuracy and precision, turns out that the fact that the nodes know that the dynamics are continuous and that they are able to follow the oscillations a little better, turns out that makes nodes be the best in the interval score category. So the smaller the interval score, the better the model is at performing forecasting. So this was pretty surprising, and we're pretty happy with this result. The nodes they may not be the most accurate nor the most precise, but when you combine those two factors, they are actually pretty good forecasting tool. And then for the community size, this one was pretty interesting because if you see the UDEs, they seem to underperform. They seem to underestimate the final community size, whereas the rest of the methods, they all seem to overestimate it. So if we go back to the figure that I showed you before, where you see that UDEs, the population trends seem to predict that the populations are going to collapse. And then we get back to this figure, and we see that UDEs underestimate how many populations are in the final community size. That's telling us that our choice of the known dynamics seems to be causing seems to be having some trouble in the methods. Just gonna pretty briefly talk about inclusion of time into training. When we're looking at nodes, we found no improvement in the forecasting performance. This could be because when we're forecasting time, we're basically letting the neural network learn that today is time 1, tomorrow is time 2, and so on. But maybe by day 10, because we're trying to forecast time, at time 10, maybe the neural network is predicting that we're at time 20, for example. So there's some error propagation that could be causing limitations, and proper inclusion of time into node models may require some more sophisticated architectures. But UDEs on the other side, they had an improvement in accuracy because they knew time. So we gave UDEs basically time is time t plus 1. So they learned that, and that helped them a lot into increasing their performance, their accuracy. So conclusions of nodes. ADM outperformed all other tested models in accuracy, and nodes outperform ARIMA models in precision and all other tested models in the interval score. And as I was saying, this is probably because because they know that we're at continuous time. Following the dynamics of the data improves precision in a way that compensates for its loss in accuracy when we compare it to EDM. So that's great news. And for UDEs, the story is a little more unfinished. What we have is that this hybrid nature, when we're trying to train the neural network, is it's inducing some sort of bias towards the dynamics. So just to remind you, we were using the shared common mortality as our non-dynamics. So that, and we suddenly, after doing all of this training, we saw that all of the populations were predicted to exponentially decline. So that's suggesting that this bias was a little too strong. And something I didn't mention is that originally we were testing these methods using not using regularization, and this was not the case. So we were actually getting UDEs were having comparable accuracy to nodes. Of course, it was worse because then we had the issues of observation noise. So we decided to go with regularization. It makes more sense as a forecasting tool to do regularization. But regularization negatively affected UDE performance, and some other papers, another paper, they suggest that we may not need to regularize UDEs. That was just a suggestion in their paper. This is an open question whether how different non-dynamics affect the performance and what the impacts of regularization on UDE performance are. So if anybody's interested in reading this paper, we just resubmitted our version, and we have a preprint online. So if you're happy to scan the QR code if you're interested in it, just gonna give a couple of seconds there. Somebody's interested. And I wanted to talk about what we learned. Like this was a lessons learned. Every basically we're just a couple of small group of researchers, maybe like 10 researchers in ecology that we're trying to learn what the limitations are for ecological systems of these scientific machine learning tools. And I'm going to talk about 2 lessons learned from this project. I just wanted to talk a little more in detail about regularization of UDEs, because we found that the spectral regularization weakens the effect of the neural network during training. And we are the second paper that talks about regularization in UDEs. And we are so So this Bolivar et al. Paper, they found that they didn't need regularization when they were using ODEs. And we're finding that regularization actually makes the model worse. So that's an interesting question. We're getting somewhere here. And their discussion briefly mentions that basically because we have known dynamics, they are providing a basis for the neural network to regularize itself. So basically, any problems caused by observation noise are absorbed by the fact that the UDE knows what the non-dynamics are. Uh, that's a conjecture. I think that from this discussion that we're having through the papers that are being published as we speak, some questions come into my mind. So, well, first one, the obvious one, is it true that the need of regularization is reduced by the node dynamics? Or is this a statement that depends on the choice of node dynamics? So what happens if, for example, if instead of using shared mortality, maybe we chose the exponential term, which is a little more complicated to incorporate into the neural network. But what happened if that, like, would that have changed the outcome of the regularization effect? That's one question that we are interested in exploring in the near future. And there's another clever loss function for UDEs that was published in 2021 in scientific reports, that it may be another way to overcome regularization. So we may be interested in comparing different loss functions as well to see what leads to better performance for UDE as a forecasting tool. Another lesson learned from this is that training the neural networks to always start from one initial condition leads to increased errors, because as the neural network gets far away from its initial condition, it slowly starts to deviate as we increase the forecasting horizon. To overcome this, we can learn, we can train the neural network to use different data points as initial conditions. So basically, we're not teaching the neural network to just predict from the first initial condition, but to predict from different initial conditions. So it has a better chance of understanding what happens at different points in the time series. And this leads to a suite of training methods called multiple shooting methods. There's, and the diagram that I'm going to present in the next slide is then the basic idea. But there's a lot of adaptations out of this idea. So here, for example, we have, I think you cannot see the pointer. Oh, okay, maybe maybe this will work. Yeah. So in this case, we have our time series all the way to time 6. So instead of learning, instead of starting always from point x0, we're learning from x0 1 to x0 to x final 1. So we're learning a small portion of our time series, and then there we're starting again at that point to continue predicting until x final 2, and then at x0 3 we're predicting all the way to x0 final 3, x final 3, sorry. And so that basically means that we're using the 3 initial conditions as the initial conditions of our neural network. And you want also to have some penalties for these gaps. So basically, you want the neural network to predict something that is continuous. So you can add some penalties for discontinuities in the prediction, and you can also try to test. You can also use different initial conditions as hyperparameters, and that way the neural network is learning the dynamics at different points, and that improves performance of the neural network itself. That's something that we have started incorporating into our neural network architectures. Loss function that tries to use shooting methods. There's a lot of developments being done on this method to come up with more efficient use of the space, or adding some redundancy to improve performance at different time points. There's a lot of things to talk about, but that will be another talk for another day. And finally, some future challenges, some things that are still under development: inclusion of spatial data into the SciML context, and the stiffness. So spatial data can already be incorporated into physics-informed neural networks. Basically, you have your neural network learn space as well, and then you put it into a PDE. So your loss function includes a PDE, and that makes you have a physics-informed neural network that has a spatial data. Of course, we know that nodes and ODEs have some benefits because we can interpret what's going on the background of the nodes. But how do we incorporate space? That's a question that's still under development. A pretty recent paper, literally published like last week, provides an example they're calling it a PDE preserved neural network, in which you have instead of having a feed-forward neural network like in the case of nodes, you use a convolutional neural network, and that allows you to learn the spatial correlations in your data. So it's basically a node, but with a convolutional neural network. And then they can compare their structure, the convolutional neural network, to a low resolution PDE, and that they are finding that when you do that, there's a lot of improvement in the performance of the dynamics. So it's a pretty promising paper. There's the reference if you're happy to read it, if you're interested. And finally, stiffness during training. Nodes can become stiff when training, even with synthetic data not produced by a stiff differential equation. This was not the case in this project, but this has been the case in some other projects that we've been working on. There's some recommendations to address stiff differential equations in this paper, but these recommendations are not foolproof. There are and Chris Rakaukas from MIT and the Julia Lab. He's been one of the leaders in the development of scientific machine learning tools, and he mentioned that some new node architectures are being under development on his wing to address the stiffness. They are on the testing side of things. Hopefully they will have some new exciting architectures coming up, but this was just a personal communication I had with him. So yeah, thank you, and we're happy to continue the discussion over email, and yeah, I'll be happy to answer any questions.
Okay, thank you. And also for the people online, you can directly raise your hand. The questions to hear in this room.
Yeah, got a question concerning the interval score. You said that the nodes specifically are outperformed by EDMs or LSTMs, and that the interval score is specifically a measure that combines accuracy and precision in some way. Can you maybe say two or more words to the in which way this interval score combines accuracy and precision, that it makes it better forecasting tool?
Sure. Yeah. So the interval score. Yeah. Actually, I didn't know this interval score. This is I'm probably this was a suggestion by the reviewers of the first version of this paper. But basically, an interval score is a relatively new forecasting performance metric. And that's basically, so the formula for it is the size of the prediction interval, right? That's the starting point of the interval score. But then you start adding all of the cases where the real data was not present in the prediction interval. So basically you have precision because the smaller your prediction interval is, the smaller your interval score is, because that's the starting point of the whole score. But then you start adding. Basically, you're keeping track of all of the data points, and every time your data point is not in the prediction interval, then that means that that is a loss of accuracy, and that increases the interval score. So that's how they are accounting for both precision and accuracy in this metric.
Okay.
I don't know if that makes sense.
Yeah, good. Yeah, thank you. More questions in the room? Any questions online? You can just unmute yourself. Okay, I have a questions then for okay, and you mentioned that you use different ways of choosing this initial conditions and try to improve the prediction. There's any guidelines that how you're going to choose that? Because you show some illustration, but there's any more practical way that we can follow as a guideline?
Yeah, so that's one of the improvements that has been done. So in my case, what I started doing in the more recent projects that I've been working on is to just do the naive case where I put the data point as my initial condition. In many cases that is good enough, but it doesn't have to be it's not necessarily the best case. So how people have been suggesting to do this is that you choose your initial conditions to be a hyperparameter. So you're optimizing not only the weights of the neural network, but you're also optimizing the initial condition at the same time.
Okay. So this way depends on the choice. Have you you have to choose the different ones or?
Yeah, because basically what I've learned is that all of the different cases of how you choose your architecture, they are all essentially contained on the loss function. So it's all a matter of how you are programming your loss function. So in this case, if you want to have your initial conditions of each of the intervals as a hyperparameter, you just add them as parameters in the loss function, and then you're optimizing both the weights of the neural network and the initial conditions as additional parameters. That's one thing you can do. You could learn differential equation and then try to do you could try to do tuning after the training. Maybe that's another way. I've been doing the naive way, and it's been working well. And the naive way is just choosing your data as your initial condition. This could be a bigger issue when you have chaotic dynamics. In this project and the projects I've been working on, we have only cyclical dynamics, so that's not a problem. But if you had chaos, maybe you want to have initial conditions.
Okay, yeah, great, thanks.
Can I ask a question?
Sure, please.
So you showed that the time aware node did much better than the non-time aware one. But that was on artificial data where you didn't have a time forcing. So I didn't understand how that worked, because you just had the artificial dynamics of a dynamical system. Or did I miss an important part?
Oh yes, sorry, I briefly went through this, but if you see the model that we were using for the synthetic data, the growth term, the growth function mu,
Yeah.
the
Oh, it has a T.
this time dependence is a real time dependence. It's not just a factor. So it depends on a function that's simulating temperature oscillations. So
I
it's a sine wave that varies through time.
Okay.
So this differential equation is actually a non-autonomous dynamical
Okay,
system.
I understand now. Thank you.
Yes.
Thank you, Pauline. And any questions? Yes, Peter.
Yes, and I have a question because you said that the UDEs had a strong bias towards the term that was introduced to them. So I was thinking maybe then, do you think it would be better to go for another approach that, for example, adds it to the loss function instead, so it's more flexible, like I think the pins do that, no? So what do you think about that? What are your thoughts?
Well, that's a good question. I haven't gone that deep into the literature of pins as forecasting tools. I'm pretty sure that a lot of people have used pins for prediction, well, for forecasting of time series. Well, I mean, I'm still pretty hopeful of UDEs. I think that at least in ecology, there's a lot of interest in having hybrid models. And by hybrid model, I mean you have your parametric models that we have used for more than a century now. They provide a lot of information, and maybe have some non-parametric estimator learn the rest of the information that we don't know. This will be an ideal scenario, and hybrid models have been proposed for the last 20 years, but until now we didn't have the computational power or the model technology that we have now. For example, these UDEs. So I'm pretty hopeful that they will be useful. They have been useful in other fields. For example, that paper that I mentioned of Bolivar and collaborators, they found UDEs to be pretty useful to predict glacier dynamics in the Arctic. So I'm pretty. What I think is that this is more a question of how we are building the architectures of the UDE. How are we setting up our loss functions? I just think that we have to address the question. We have to address the small technical questions that maybe are painful to answer. So we can kind of come up with good practices. So here in the work I presented today, I basically we learned that regularizing UDEs like I did was not a good practice. Maybe it would be the story would have been different if I had chosen a different known dynamics function. That's a question that we're exploring right now.
Yeah, very interesting. Could I also a related question, very good one. What software did you use for that?
Yes, this is all in Julia. Yeah, Chris Rakaukas, I think he's the CEO of Julia Lab. So Julia Lab is one of the one of the main developer groups of the Julia ecosystem, and they have made pretty easy to use libraries for scientific machine learning tools.
Thank you.
Good to know. And any questions here in the room? And more questions online? Yeah, great. Let's thank you and thanks our speakers again. And I have announcements that that's for the